Welcome. Today we will learn, or I will talk about the combination of machine learning on the one side to address causal relationships on the other hand. So that's the current research example. Oops, don't know. You can see the slides. Well, I just keep on going. Okay, let's start again. So today I will talk about the combination of machine learning and causal analysis. Why? Because that's very important in various contexts. I mean, either if you work in the business context, then you have managers asking you about the causal effect or the positive or negative business impact of selling certain products and certain services. Or if you work in the technical context, such as, let's say, maintenance, technical maintenance, you also wonder about optimal interventions. So I think causal relationships is something that most of you will often see in their own work because, it's important to make good decisions. In order to make good decisions, it's important to have an idea on the causal relationships. Okay, so today I will start with a little bit of a motivating example, which is based on a project with Booking.com, and I think most of you will kind of relate to this. So you know that Booking.com is not only a platform to book hotel rooms, but also to do more. So cross-selling is a big topic in marketing. So probably when you came here to Oporto and you booked a hotel room, you were probably offered not only the hotel room, but also some additional stuff, like experiences. You know, a nice boat ride down in the river at night, I don't know, candlelight, whatever. You know, all these activities that you are asked, do you want to buy this also on top? Okay? That's a service that companies like Booking are offering, but they internally ask themselves, well, is it really beneficial for our business? Okay, so it's a causal question. They just wonder what to do. What's the best way to, let's say, increase interactions with users? So in that case, the causal question was, does cross-selling these ancillary products actually help me in terms of my business? And here you try to quantify this, so you see whether people book something, like an additional boat ride, and whether they have more bookings of accommodations, like hotel rooms or whatever, in the follow-up period. So that's basically sketching that causal question from the business perspective. And I guess most of you will have some kind of idea on such relationships. Well, how do you do this? So many of you might know experimentation. So you run A/B tests, and maybe you can offer some people some products, and some others you just exclude them from that. That's an easy way to run an experiment and to assess causal relationships because you don't have to think about any kind of complication that might come from the real world because you yourself, you have a device that's assigning some people to some version of your website or the app, and on the other hand, some people are excluded from that. So that helps you. However, in many cases, this is not feasible. For example, in the case of the bank from before, they are probably not willing to randomize credit lines, right? Because probably it's maybe a little bit too expensive. Sometimes experiments are just like not ethical. And I think, so my opinion on that is that in many cases, the more important business decisions, they involve something that you cannot randomize. Because, for example, you have standard services that you are selling all over time, and you just cannot shut down these services for some types of the customers, right? That's just against the proper purpose of your business. So let's assume you're in a situation where we cannot run A/B test. So there you have to live with the data that you have in your database, which is basically observed data from past transactions. And I guess most of you who have ever reported on, I don't know, statistical report on customer insights, whatever, business and marketing, you always see this claim, you report a statistic based on descriptive analysis, and then people say, well, I can see something in the data, but is it really causal? Okay. So today we will talk about that causal thing, the causal interpretation of statistic results. So that's one part of the causal machine learning topic. The second part is combining machine learning tools to address such important questions. Okay, so this motivating example about cross-selling boat trips here on the river in beautiful Porto is just one example of an important business question that you cannot answer generally. You cannot just answer generally by running an experiment. Instead, you have to use tools from causality in order to think about, well, is this correlation maybe causal? Is it not causal? How do we do this? And here, it looks easy because it basically only contains 2 steps. But especially the first step is pretty tricky. Okay, so first of all, you get some kind of problem. As before, you have someone who comes to you with a request. He says, well, I wonder about that thing. Should I shut down the service or should I invest in that service? Should I improve my services? Should I lower my prices? Whatever, all these kind of questions that you get on a daily rate. The challenge is now to really pin that down in a causal quantity, which is something like a quantification of that causal parameter. I mean, the standard example is a correlation or the output of a regression, a test, statistical test like a t-test, whatever you have. The thing about that causal stuff is that it's something that's not observable in the data, okay? You will never be able to ever observe a true causal effect. And that's the fundamental difference to predictive machine learning, where you can always benchmark your predictions of the model against the ground truth that you see from the true observed labels in the data, right? Here it's different, and now I will try to explain to you why that is. That comes down to the question how you would ever yourself define a causal effect. So the causal effect is the change in one variable that can be attributed to a change of another variable. The variable we would like to intervene on is called the treatment variable, which would be like selling another product. Okay, so I would be a treated person, that's the language of causality. I would be a treated person if I do not only book accommodation, but also the boat trip. I would not be treated if I do only buy the accommodation, but I don't do the boat trip. So these are 2 potential states of you, and more or less you can think of that as 2 potential states of the world. And you have to think about this potential characteristic of the world in order to define a causal effect. Why? So let's assume someone here, I don't know, I pick you, you sit in the first row. Okay, did you do your booking through booking.com? Yeah, now you have to nod. Yes, yes. Did you buy a boat trip? Did you buy a boat trip on the river? Yes. Okay. So this person apparently did buy this additional product, so it would be a treated person. Now I can look at the data 6 months from now on and count how many times he came back to booking.com's website and booked another accommodation. Okay, that would be quantification of my success of my treatment or whatever. The problem is, I can only see what actually appeared in the real world, but I could never see what would have happened to this person if he had not purchased that product. How many bookings would you have done had you not taken the boat ride here in Porto? Okay, so that's somehow, it's called a fundamental problem of causal inference. It's a little bit complicated. What it basically says is that you always observe only one state of the world, and the other is counterfactual. You can see in the data whether someone has bought a product or not, and how many nights he slept in a hotel in the next time period. But you cannot see what would have happened had he not did this thing. But this would be a crucial thing in order to define a causal effect, because the causal effect for you would be a difference in the terms of the number of nights that you book now in the next 6 months, only because you book this additional product. This would be the causal effect on the individual level for you personally. And you can do it for everybody here in the hall. So this is bad news, and it makes things complicated, but there is hope. Okay, and the hope is we can go to another level. when we can't talk about individual treatment effects, we can leverage up. We can go on an aggregated level and say something about populations. And that's actually the reason why experimentation works that much. Okay, so in an experiment, you all had to take a boat ride tonight, you have to book it through booking, and you were the untreated, you can't book it. Okay, I decided, or I flip a coin, and you have a treatment assignment, randomized experiment. I calculate the average of accommodation bookings for you, and for you, I take the difference. That's an estimate of the causal effect. This is how randomization and experimentation works. Okay, but as you see, this is not possible. So what I have to do is I have to take the second step. I have to talk explicitly about assumptions. So causal inference, causal statements always depend on some kind of assumptions. Such an assumption can be, well, I'm in a lucky situation, I can run an experiment. Okay, if you do it right, happy to go, you can say something causally. If you can't, you have to make different types of assumptions. So these assumptions are very, very important in causal modeling, but there's more. So this was the causal part. Now we come to the machine learning part. We also have to estimate it. You can run correlations, whatever you do, linear regression, or you can do a little bit more fancy stuff and work with nonlinear learners for machine learning. You can use unstructured data, you can use deep neural networks, whatever you like. So this is why we talk about causal machine learning. So first of all, here in that case, we try to find definition of a causal effect. So there are various measures how you do this. Sometimes a correlation would be enough. Sometimes you talk about risk difference, whatever. Here in that case, there's one parameter which is called the average treatment effect for those people who actually were treated. So that's basically measuring the average causal effect of selling some additional products on the aggregated level if I consider only those people who actually bought the additional product. Okay. Why is that important? That's the relevant quantity from the business perspective, because it actually helps to measure or quantify the average impact on the bookings that come up in the follow-up periods that come exactly from that auxiliary product. It basically answers how many nights more do the people now book with us had they not, as compared to the case, had they not booked the additional product. It's a little bit philosophical, hypothetical. That's the type of part of the game in causal machine learning. Assume you have some kind of measure. It's basically a metric that you calculate. When can you talk about causality? And this is related to the topic of causal identification. Basically clarifies there's a formal way to justify when something is causal or not causal. And this is related to some kind of assumptions. And one of these assumptions is called unconfoundedness. So it basically says there's no other force at play that is going to explain my observed differences in the outcomes. Okay, so you have some kind of a correlation, let's say, and you wonder, well, do I account for all the other things that play a role here? Is it causal or not? Yes or no? So here, this is why we have this funny graph. You don't have to read it, it's a little bit small. This funny graph is basically kind of mimicking the causal relationships that are at play here. So business travelers, I know you are all here for leisure, but there are also some people who travel for business. So they have just different behavior. Maybe they're not interested in boat rides. Maybe they're just like, only sleeping and then they go home. Maybe that plays a role here. You have something like loyalty consideration. You have customers who just like the services provided by a company and they just buy everything that's provided by the company. All these things, these are causal relationships that you have to account for. If you don't do this, you will measure something like a statistical estimate, but it will reflect some biases that come from these selection mechanisms that are at play. So actually what you measure is maybe just people spending their time. So you measure something like a leisure effect. Or you just measure the loyalty of people instead of actually the causal effect of that cross-selling. So that's something that you always have to keep in mind when you talk about causality, causal machine learning, that there are some assumptions, there are some things that you cannot estimate. So there's always a human at play here who has to judge whether something is causal or plausibly causal or not. And here, there's another step of estimation. And estimation is the part where machine learning comes into the game. Okay? And I talk about causal machine learning, but here I especially focus on an approach which is called double machine learning. And the following, I'm trying to give you a little bit of an idea what's happening and what's the challenge here. So let's assume you all know about, background effects, so-called confounding. There are some things, biases that make causal statistics non-causal, all that stuff. Now we are ready to go. We have the data prepared. We have the causal diagram. And we want now to estimate it. Well, what can you do? You go to ML engineer and say, yeah, we have this problem, this data, just estimate causal effect. What would they do? They would maybe run something like various estimation steps, just plug in off-the-shelf methods, gradient boosting, whatever you like, deep neural networks for different types of data, as you like. You can be creative on that. The bad message is already stated here. So these methods are generally not employable for causal statement. Why is that? That really goes down to the point why machine learning is working at all, why we are all here talking about AI and all that stuff. So the ingredient that makes machine learning so fancy, so interesting, is that it imposes something that's called regularization. What you do is you create a very, very complex, complicated models that's hopefully mimicking or learning some complex relationships in the data for predictions. And that complexity is the reason why we want to use it. Because it's just better than linear regression, right? It's better than logistic regression, all that stuff. It can model nonlinearities, it can use unstructured data, text data, image data, whatever you like. Well, there's nothing for free in this world, so that great complexity comes with a price, and the price tag is so-called regularization. So in some kind, you have to limit the complexity, the flexibility of these models, because otherwise they would always overfit. So machine learning are inherently limited for causal inference because of regularization. Let's think of lasso estimation. So lasso estimation has an explicit penalty that's going to bias downwards your estimated coefficients, right? You can imagine that this bias would also distort your causal estimate that comes from just like off-the-shelf use from lasso regression. So what you have to do is you have to take that into account. So just, again, the bigger picture, causal machine learning is basically combining the stuff that we know about the causal inference that comes with all the assumptions. There are formal frameworks. There's a big literature. So I have background economics. This is what I learned in my bachelor studies, right? On the other hand, you have all these great tools for machine learning. And for a long time, it has been a question, it's still ongoing research, how can we combine these two things? Why? Because both of them are helpful. Causal statements are important to make decisions. Machine learning is important to generate good predictions. Double machine learning. It's one approach for causal machine learning. Why do I talk about this? Because it's a very general approach. It covers many different causal scenarios or models that you would like to run and estimate and practice. And it also has a nice structure, which is based on 3 key ingredients. So the first one is so-called orthogonality. And that's the most important and most tricky one. As I said, regularization is the limitation for the use of machine learning for causal statements. Orthogonality is a way to handle that bias that comes from regularization. It kind of reformulates and restructures the causal estimation framework in a certain way. And the third and the third ingredient is something that you probably know from machine learning. You should always split the sample, and you should use good learners. At least loosely speaking. So this is just kind of a statement that I hope you can take away from my talk, is like double machine learning adapts the inferential framework, because at the end we want to have a number, a confidence intervals ideally, that's showing us some evidence, or it's pointing us at the value of the causal effect that we would like to know. This adaptation makes it possible to work with machine learning, which says the regularization bias is kind of managed in some way, in a way that it will not introduce a bias to the causal estimate at the end. And the key ingredient here is so-called neighbor orthogonality, and I have an example at the end. So what is causal machine learning? Well, that's it. It's basically output from a regression. This is something that you probably know, but or it looks like a fancy way of reporting correlation. But what's hidden here is that basically the entire estimation was based on gradient boosting, and you can also do it with any kind of machine learning tools, as long as your double machine learning framework accounts for that regularization bias. Okay, so just to sum up, before we come to maybe in-depth presentation of orthogonality, it's like overall double machine learning is a very general estimation framework for statistical inference. So it's really giving you something like a consistent estimator, which is not biased in the limit. You have confidence intervals that satisfy certain nominal coverage, as you know it from maybe basic statistics, linear regression. And the causal part comes from the assumption that you make. Can you make sure that there's no selection at play that would explain away your causal effect that you find? Okay, so that's always something in the causal machine learning part that will be there. So here, also in that project, a very important part is to really talk about the causal model, especially with domain experts. Nothing that you can just give to ML engineers and they train a causal model. No, instead you have to come up with a causal story. It's kind of an abstraction of the causal problem, systematic biases. So that was basically the basics. However, there's ongoing research. There's also more that causal machine learning can give you, something like very detailed and fancy ways to model heterogeneities, like subgroup effects. There are different study designs. Maybe some of you might know encouragement designs. There's also double machine learning for that. You can also think about robustness, how much you can stretch your causal results from a causal analysis if you think that maybe you're missing something, like a background variable that might actually be reflected in your causal estimate. And of course, you also have new types of data and new types of insight that you could use, especially if you consider unstructured data. So what information is contained in images? Imagine booking.com. I mean, you probably look at the images from the hotel before you book it. You look at the comments. Well, now with machine learning, deep neural networks, you can account for that. You can account for that in your causal model. But that's something that's ongoing research. And the last point, which is probably the most important part, is like really applying it to real-world problems. Because, as I said, it's a huge promise to say, I say something about a causal relationship, but at the end you are never sure whether your assumptions really hold or not. So bridging that gap between a formal theoretical framework and a real-world project where you might be accounted for, yeah, it's two things. So thank you very much for your attention, and now it's time for questions.